Okay, using my numbers, the third problem. Gives you a height function. So I toss this up in the air. This function tells you after t seconds how high it is. Okay? I'd have to toss it up quite a bit faster. I'd have to toss it up at about 33 miles an hour. And I used to have a fairly strong arm, but I can't copy it anymore. I might have been able to achieve a vertical 33 miles an hour. Okay? Probably could. Probably could. Okay? And the height of 1.5, the height of, we want to find the height when t equals 1.5 and when t equals 2.6. Well, height when t equals 1.5, if t equals 1.5, we plug in 1.5, right? So we can say that h of 1.5 equals -5 times 1.5 squared plus 15 times 1.5 plus, yeah, that can't be t. And we got L, but I have no letter close to the L, so I don't even know what that should have been. I'm just going to make it 1. Okay? Yeah.
-5t squared plus b times t plus f.
I mean, printer's not that, oh, that's F. And the stupid apostrophe is too close to the F. I can't see it. Okay, well, in my case, F is 11, so that's convenient. Okay. Don't have to erase anything. Okay. Now this is then 1.5 squared is 2.25, and you multiply this out and you get -11.25. And then this is 22.5 and this is 11. And that adds up to 22. Not 22.25. Okay? So it's 22.25 meters high after 1.5 seconds. Now that's something in the neighborhood of 70 feet. Not sure I could throw something 70 feet high. Pretty sure I couldn't. But I could throw things. I don't know. Seems a little high, but h of 2.6 is, and I'm just going to write out what it is approximately. 2.6 squared is 5.76. Everybody knows that, right? Okay. And you multiply that by 5, and you get 25, and 25, pretty close to 20, maybe about 29, and I'm fudging a little bit. And then this is 24, so it's -29 and 24, which are like -5 and 11, so it's about 6. And you can work out the details. That's why I let you use calculators in this, right? And so you probably need a calculator for this. I think it's pretty close to 6, though. So assuming this is true, that's easy, right? Okay, that much is easy. You just plug in, do the arithmetic, or in this case, you let the calculator do the arithmetic, because I know you can, after you've got it plugged in, I need to see this. I don't want to just see an answer. I need to see this. But then you can just say equals whatever. Maybe put in parentheses calculator or something like that, but that's legitimate. Okay? And similarly here. Okay, so now, average rate of change of h with respect to t is change in H divided by change in T. Well, H changes from 22.25 to 6. And this is an approximation, the 6 is approximated, but it's about 6 minus 22.25. And the change in T is from 1.5 to 2.6. Okay? This is approximately what? That's about negative 16. And this is about 1.1. Okay, and 10% less than 16 is about 14. So I'm going to say about 14. Okay, negative 14. And actually, I'm going to change this a little. I want to write for reference. Okay, this is this, and what does this mean? Well, H is in meters, right? So this is negative 16.25 meters. Divided by 1.1 second, which is approximately negative 14 meters per second. What this tells you is on the average, now this thing's falling, right? Because the change in height goes from 22 meters to 6 meters, falls about 16 meters. Okay, about 50 feet, height of a medium-sized tree, okay? Further than you want to fall because you can die. Incidentally, you know how you die when you fall? I mean, if you fall wrong, you can mess up your internal organs. But I've seen that the primary way is the way your head snaps when you hit, you fracture your spine in the thorax. Okay? So, bottom line is, if you can avoid falling from 50 feet, please do. It can be survivable, but usually isn't. Okay? If you're going to fall, fall from 1 or 2 feet and try to land on your feet. Okay. Just, if you got a choice. Okay, well, I know what choice you take, that's automatic, but, okay, so anyhow, you're falling at an average of negative 14 meters per second, which is a little over 30 miles an hour. Of course, when you start falling, you're up higher. When you finish falling, you're down lower, so you're going faster, right? Because everybody understands that as you fall, you speed up. Okay? So your average is about 30 miles an hour, but at the end of that fall, you might be going 50 or 60 miles an hour. Okay, so there's an interpretation here. And this is why we study these functions, because there's an interpretation. And one of the simplest interpretations is height versus time. And you do get a quadratic function. I could explain the physics to you, but it would take a couple of weeks. And this is a physics course, so we're not going to worry about that. There are also applications, as you've seen if you've done the homework, to revenue versus selling price, or profit versus selling price. You get quadratic functions in the simplest linear model. A very useful model for deciding how to price something, if you have the data, okay? So from business to physics and everything in between, you end up seeing a lot of quadratic functions, okay? Okay, well, there we have it. This is the average falling velocity. For t from 1.5 to 2.6, which means on the time interval 1.5 seconds to 2.6 seconds. Also, the graph of this thing is a parabola. If I want to graph this, if t equals 0, h is 11, meaning 11 meters, right? So I know that I'm going to go at least as high as 22.25 meters, right? So we've got 11 and we've got h in meters versus t in seconds. Looking at the graph gives us a picture of this whole calculation and the rate of change. So we've got a height of 11. When t equals 2.6, the height is down to 6. So if this is 11, 6 is a little over half of that. So this is a point on the graph. Okay? This is a point on the graph. When t equals 0, h is 11. And when t equals 1.5, which is, 1.3 would be halfway, so 1.5 is a little more than halfway from 0 to 2.6. The height is 22.25. So we'll just put 22 up here. And this is going to be that, just a little higher than 22, and you can't even really see how high on this scale. Does that make sense? Okay, so we're going to go into a little bit about the graph of this function, a little bit more, but what you can see right now is that if we do a straight line segment, there's all my chalk right there where I can't see it. In other words, in plain sight. To get the average rate of change, I can just do this fundamental triangle. Didn't leave myself room, but this is negative 11.25 here, and this is 1.1. So the slope is, it's not 11.25, it's 16.25. I'm going to fix that. Okay, right there are the numbers, right? But the rise goes from 22 down to 6, 22.25 down to 6, right? So if you go from 22.25 down to 6, you see why this is negative 16.25, right? And if you go from t equals 1.5 to t equals 2.6, we see why the run is 1.1, representing a fall of 16.25 meters in a time of 1.1 seconds. Well, then the slope is approximately negative 14. So again, this reinforces the idea that the average rate of change can be represented by the slope of a line segment on your graph. And this is extremely important when you're beginning a calculus course. And all the way through the calculus course. You've got to have this picture in order to understand what the calculus is doing and what it's telling you. Okay? Well, there we have it. Now, let's look a little bit more closely at this graph. This graph, and I'll draw it again because I don't want to get too cluttered up with what I've just done with the fundamental triangle, but you've got this point, and this point, right? The graph is a parabola. It has exactly the same shape as your basic x squared graph. Exactly the same shape, but maybe spread out a little bit or compressed a little bit or stretched a little bit, right? But the shape is what the shape is. And you could always draw an x squared graph at a scale that makes the shape fit these 3 points. I'd have to turn the shape upside down, but the point is you can always draw a parabola through any 3 points as long as the x coordinates are all different. If the x coordinates are the same, then one point is vertically up or down from the other, and you can't draw even a function, right? Because you fail the vertical line test. Okay, so what I'm going to ask you to do is sketch that picture as accurately as possible without taking 10 minutes to do it, okay? So a quick 1 minute picture, but as accurately as you can make it, showing all the aspects of the relative positions of these points, and draw a parabola that appears to fit the points. Now I'll give you a hint. This point is further over, well, this x coordinate is closer to this one than this one is to this one, right? So the top of the parabola ain't going to be there. It'd make it lopsided. Okay? Top of the parabola is somewhere else. So don't try to put the top here. Okay? Try to draw a parabola. You know, has the shape of the x squared function. Of course, hopefully you've drawn a lot of those. It looks something like this. Okay? But spread it out, turn it upside down, and see if you can make it fit these 3 points.